Dear participants of the MicroCAD 2022 meeting at the Kharkiv Polytechnic online. Welcome to the meeting. I'm very happy to see that you're maintaining scientific meetings in these difficult times, because science is international, and it's an important thing for Ukraine to continue to participate in these difficult times. Ukraine carries forward some of the great legacy of science from the former Soviet Union, and Ukrainian scientists must do their part in rebuilding this as Ukraine's contribution to future science. I'll say a few words about my subject of interest, the hope for a topologically protected quantum computer. And the key message here, which maybe will resonate with people at the meeting, is that as we understand quantum mechanics better, new and strange possibilities for the materials of the future and the technologies that they will allow are starting to emerge. And these understandings have really come from unexpected discoveries that have led us to new ways of thinking. So around about 1980, the subject started with two apparently independent discoveries. One which I participated in on quantum spin chains, and of course a much more important one on the quantum Hall effect, which Klaus von Klitzing discovered. And these are all things in which quantum mechanics and quantum entanglement plays a key role. And the main point of this is they were completely unexpected discoveries, and these results were surprising to everyone at the time. And no one knew that these things were waiting to be discovered, so it took luck to do the experiment in the right way with the right protocol, or think about the right be thinking about the right problem to even allow these kind of ideas to emerge. And we don't know who will make these discoveries, where they'll be made in the future, but except they will come from a place which participates actively in international level science and maintains scientific tradition. So people are thinking about these kind of problems, and some will have the chance to stumble on the right direction to make these unexpected advances. So around about 1981, I discovered this spin one chain of spins, quantum spins, could have a novel state, which is now understood to be the simplest of all the topological states. Before, people hadn't really thought about entanglement and thought of magnetism in a very kind of classical way, where you just assemble a load of atoms with their spins pointing in various directions. But it turned out that the system had a new kind of quantum state where the spins entangled by somehow splitting them in half and coupling with their neighbors. And the strange result, which is typical of topological physics, is that unexpected states at the edges of the system occur. In this case, free spin one half states at the edge of a system which was only made out of spin ones. And the meme for this is hands come in pairs, but if you line up people in a chain and everyone joins hands, there's still these free single hands at the end of the chain, which is sort of how the system works. And this turned out to be the very simplest of case of topological matter that's recently been classified much more fully. And the more important and clearest discovery of topological states was initially the integer quantum Hall effect discovered by Klaus von Klitzing. And topological systems also have this property, as well as having edge states. They have quantizations which involve pure numbers. And this, of course, has led the quantum Hall system to become the part of the basic system of international units. It was much more interesting discovery after the initial one. Another surprise that you could actually have fractional quantization of the quantum Hall effect. Again, that was something that was unexpected, and it took a lot of thought to work out what could be going on. And this led to an unexpected new kind of wave function discovered by Bob Laughlin. Even more remarkable than these early fractional quantum Hall states are something called non-abelian quantum Hall states, which are now believed to, on paper, support universal quantum computing, but haven't yet been fully demonstrated experimentally. These allow hiding and processing of quantum information, and braiding little defects around inside the system is a way of changing of processing the information. And again, these are very surprising ideas. And in the quantum Hall system, the system is manifested by fractional vortices in these quantum Hall fluids. And the configuration of these vortices contains entanglement information that you can't see, because it depends on the history of how various configurations were created. But by moving these things around, you can process this quantum information in principle. So the quantum Hall systems which produce these non-abelian states have been seen experimentally, but have been very difficult to work with. And it emerged that this whole idea of these different defects which allow information to be hidden in the quantum material is related to Majorana zero modes. And those can occur in other contexts too. And the basic picture here is that an electron can either occupy or not occupy an orbital. So an orbital which has two possible states, which is either empty or filled with one electron in this case. And the Majorana zero mode is a curious thing where you're able to pull apart an electron orbital into two half orbitals, which is a very strange idea. It's even stranger than pulling apart a spin one into two spin halves. But it's at the heart of the ideas for building a topological quantum computer. And this is following up from Majorana's discovery of the Majorana fermions in 1937. So this is a part of a beautiful dream of a topologically protected qubits. It looks very good on paper, but of course, other things like fusion power look very good in principle too. And there are a lot of technological and material issues in whether one can actually produce this. But I believe in future, there is a realistic chance that we will be able to do something with topological quantum computing. And how does it fit in? Again, in the Kitaev's model of a superconducting chain, you see that coupling, a chain of atoms coupled to a superconductor allows the orbitals to split into Majorana pairs. And the interesting thing is you can split these orbitals up into half orbitals, and then they can be reorganized so they rejoin to form regular orbitals, but again leaving half of an orbital at the end of each side of the chain, very much like the old spin chain. So these are very surprising ideas, and they're part of the quest for quantum computing. I don't know what will finally emerge in quantum technology and quantum information processing, but this is part of what we're calling the second quantum revolution, and we're bound to have very interesting things as people investigate quantum materials. The important thing is that different communities have to talk with each other. The key ingredients here are toy models, which are the kind of things that Kitaev builds or I worked on. There's cutting edge material science that's needed to bring this to reality. And there's also deep mathematical understanding of the principles which underlying all this. And, this is an international enterprise. Now, my motivational message here to student audiences is that the things which launched all these interesting ideas were unexpected discoveries, and they can be made by almost anyone who's working in fundamental science, because the good discoveries are out there waiting to be made, but no one knows that they exist. So you don't find them by being smart. You find them by being lucky, by thinking about the right kind of problem, doing the right kind of experiments, and discovering something that quite remarkable that you didn't expect. Of course, you do need the preparation as well as luck to recognize what you found as remarkable. And you need commitment to follow it through, because there's a lot of pushback when something new occurs. But basically, anyone working in science anywhere in the world, provided you can be connected to the current ideas of what's going on in science, has a chance to participate in these discoveries. And very rarely something extraordinary will show up, and you can end up with a Nobel Prize. But of course, the main thing is that you have to be working and participating in science, and who knows what will happen. So again, thank you and good luck to the conference.